Right, for today, let's discuss the gravity method. First, let's discuss Newton's law and the gravitational potential. The law of attraction is all about your gravitational force F as expressed in newtons, right, between two masses m sub 1 and m sub 2 is as follows. So their gravitational force is proportional to to both of their masses and inversely proportional to their distance. Right? So the heavier your objects are, the bigger the gravitational force. Now, for the case of the Earth and an arbitrary object, say for example me, all right. So the Earth uh is massive in terms of mass. Right? So I am also technically attracting or exerting a gravitational force, and I'm also technically trying to pull Earth towards me by the virtue of my own mass. But the Earth actually has a very large mass, and when we are talking about Earth's gravity, uh, it's only Earth's gravity that really, it's only Earth's mass that really matters. Okay, so this force here is almost all about the Earth. Right now, so gravitational force is a result of two bodies attracting each other. Although, of course, Earth is the dominant body here when we are talking about Earth's gravitational force. Now, when we are talking about gravitational potential, we are just talking here about uh, the potential due to Earth alone. So, in gravitational potential, you just remove the mass of that arbitrary object. All right. In other words, gravitational potential is also just gravitational acceleration. All right. So this big V is also your gravitational acceleration due to Earth. And that is the main concern of gravitational survey method. Right? We are interested in the gravitational potential or acceleration due to gravity. Right, now let's discuss about or expound the gravitational field of the Earth. Now we have a concept called the geopotential and the geoid. Okay, so the Earth exerts gravitational potential due to its mass. Although there's another factor which is exerting acceleration, which is the centrifugal acceleration of the Earth, or mainly due to the rotation of the Earth. Okay, so whatever gravity or whatever uh, geopotential or geo acceleration that you're experiencing, it is due to the mass of the Earth plus the centrifugal acceleration due to the rotation of the Earth. Okay, so it's a two-part acceleration. Now we have a term called the geoid, which is an equipotential surface, right? So it's a surface where you have more or less equal gravitational potential, or where you have equal geopotential or equal net gravitational acceleration. Now note that this geoid or this geoid surface or geoid level, depending on whether you're talking about a 3D surface or a 2D level, this is normally approximated by the mean sea level or MSL, but it's not exactly the mean sea level, and we will be discussing that later on. Right? So note that ocean is fluid and it has a more or less constant density. Hence, it is readily influenced by the geopotential consistently, and it's normally used to approximate the geoid. Right? The other reason for approximating the geoid by the mean sea level is that it's fairly easy to measure or determine the mean sea level when we are doing surveys, right? But remember that mean sea level and geoid are not equal. They are close, but they are not the same. Right? So why they are not the same? Let's talk about the international gravity formula. Right? So yeah, geoid and mean sea level are not the same. The Earth has a lot of irregularities like changes in density, changes in distance from the core. All right. But mainly their geoid and mean sea level are not equal because the distance to the center of the Earth or the distance r is not consistent. Right? For example, when you are in the North Pole or in the South Pole, you are actually closer to the center of the Earth. Right? This is mainly due to the bulging effect. Right? So the Earth is spinning. Sorry. So it is spinning or it's rotating, and it is partly bulging towards the equator and flattening towards the poles. Right? So at the equator, we are farther away from the center, but from the poles, we are closer to the center. So going back to the Newton's law of attraction, gravitational acceleration, the smaller the distance, the bigger the gravitational acceleration. Right, so yeah, so what the scientists did is that they agreed upon the international gravity formula, which aims to model the this distribution of gravitational geopotential or the gravitational acceleration through the Earth. And what the IGF models is mainly just the polar flattening. Right? So what the only thing you have to input in the IGF is the latitude. All right? So your latitude is your so at the equator we are at zero latitude. As we go far away from the equator, be it north or south, the latitude increases. All right. As we go to the North Pole, we are at 90 degrees latitude. At the South Pole, we are negative 90 degrees or 90 degrees latitude. Right. So all you need to input in the IGF is latitude, and from there you can obtain the ideal gravitational acceleration at mean sea level. All right. So anyway, so now let's talk about the ellipsoid. Ellipsoid is the idealized 3D shape of the Earth. So it's like an ideal shape, like the way you have an ideal shape of your face, like minus the acne, scars, and pock marks. And the ellipsoid is chiefly used for geodetic surveys. All right. To summarize, we have the geoid, which is the geopotential surface, and this is what we want for the gravity surveys. But in the field, it's easier to get the mean sea level, or it's easier to determine the mean sea level. So we use it to approximate the geoid. Then we apply the IGF, all right, to get a precise number of what should be the gravitational acceleration of the mean sea level. All right, because this is our reference point. I mean, the geoid is our reference level when we are doing gravity surveys. And it's important for us to know that number because most of the gravity surveys that we do are relative measurements. Okay? By relative, we always have to have a reference number and a reference level. So anyway, ellipsoid is a stuff for the geodetic engineers. It's just in the ideal smooth shape of the Earth. Okay? And the role of ellipsoid in gravity surveys is that ellipsoids help us, or rather, uh, geodetic surveys are integral to gravity surveys, right? And geodetic surveys need an ellipsoid model to properly make a systematic measurement or determination of the coordinates of their surveys. So in a way, we also need the concept of ellipsoid is also relevant to gravity surveys, right? So this is the IGF formula, IGF 1980. So the practical use of IGF is when we are doing regional surveys. By regional, we are talking about surveys that are exceeding a distance of 100 kilometers north-south. Okay, so if you have a survey that is like going from Bicol, or rather the south, about the southern part, mid-southern part of the Philippines, to, for say for example, Ilocos, that will be approximately in the ballpark of I don't know, maybe 600 kilometers or more. So for that kind of survey, you will be needing an IGF correction, okay? Because you have exceeded 100 kilometers north-south of survey, which is more than 1 degree latitude. Alright, so you need to know the correct value of, or the correct gravitational acceleration at the mean sea level at different stations. So this is the IGF, alright, and the only input you need is just the latitude. Alright, so just put in the degree of latitude here, and you will eventually get a number that is representing the gravitational acceleration at the mean sea level of that area, or of that location. Okay. Now, if you ask, okay, so this I just posted here a website where you can uh, automatically calculate the local gravity of a given location, and you can even input the height. All right. So this example is this latitude is the latitude of Manila, and I inputted a height of 0 for the mean sea level. So the local gravity in Manila is 9.7836, all right, meters per second squared. Now let's talk about how we measure gravity. All right, as discussed earlier, we are only concerned with relative measurements in gravity survey, right? That is most of the time we are relying on relative measurements, and we do this, or how we do this is we always use a base point or base station or base net or whatever. So anything that's a base. Okay, so we always have a reference point. So the star, so this is our reference point, and then we go to that point, we do some gravity survey. All right. So that point, or that base point, is typically an established area or an established point, and it will normally have a calibrated gravity reading. Let's say 9.8 um, meters per second squared. Okay, so it has a calibrated gravity reading that was done previously by geodetic engineers in tandem with geophysicists. So that base point has an established absolute gravity reading. And what we do during the surveys is we just put our gravimeter in there and read out the gravity. So let's say we get 9.8, right? So what we do is we just calibrate our instrument to that base level. So we just subtract like point zero 0.02 on our readings. All right. So all the future readings in our survey will be subtracted by point zero 0.02. Oh, sorry. So what the first thing we do here is we calibrate our gravimeter such that it will read 9.78 as well. So it is calibrated with the base station. All right, and then in the next surveys we will be measuring the gravity readings in other areas. All right, and then after doing the surveys, we will also subtract this value from those readings so that we only end up with the relative differences in of gravitational acceleration in those areas. So if in those areas you get a difference of 0, it means that there's nothing special in that area if you're getting a gravity difference of 0. But if you're getting a gravity difference that is positive, it means that there is a dense object that is lurking beneath in that area. Or if you're getting a getting a gravity difference of negative, it could mean that there is a light object or maybe even a cave lurking in that area. So we will be discussing that later on in the other slides. But this is just how gravity readings work in general. So you calibrate, and then you take measurements in an area, and then you subtract the gravity reading from the base station so that you only end up with a gravity with a with only the difference, a gravity with a different a relative value, okay, relative to your base station. All right. Uh, yeah. Or the simplest way to do this is to just go to the base station and set the gravity reading to 0, And from there, once you go to the other places, you will instantly get the gravity difference with respect to that base station. Right. So after taking all those readings, we also apply corrections, which we will be discussing later. And our final product is the gravity difference between the base station and the survey points, and we call that anomalies. Okay, so we use it like positive anomaly for a positive difference, negative anomaly for a negative difference, right? And these anomalies tell us if there is a change in the density within the Earth, or there's a change in density in the crust of the Earth in those areas. So when we are talking about the crust, we are talking about somewhere between a few meters and a few kilometers. Okay, and remember that in also remember in gravity that the most basic info that we get uh, is the horizontal changes in the density. All right. But there are other info that we can obtain from gravity, but I'll discuss that later on. But yeah, the most basic stuff that you can get is the changes or the horizontal changes in density of the Earth. So for example, like sedimentary basins that are surrounded by a basement rock, uh, or surrounded by dense mafic rocks. Now, in terms of units, gravity anomalies or gravity readings are expressed in either meters per second, but this is too big. This is too huge. It's impractical. We also have micro micrometers per second, or which is also called GU or gravity units in the System International. And then we also have the old unit called milligals, which is named after Galileo Galilei. So milligals is supposedly an outdated unit for gravity measurements, but people still use that unit. But for the sake of conversion, 1 milligal is equal to 10 gravity units, or also equal to 10 micrometers per second. Now, to give you an idea of how big anomalies can get, when you're talking about salt domes, oil-bearing structures or bodies, and undulations in your subsurface rock strata, these anomalies can range from tens to hundreds of gravity units. Okay, so that is um, those are very small numbers, right? Relative to the gravitational acceleration of the Earth. All right, now let's talk about the equipment. There are many types of gravimeters, but at the moment, due to the monopoly of the equipment, the only relevant equipment right now is the unstable type of gravimeter. Okay, so these are called unstable or astatic, right? And they are called so because they have a weight, right, that is supported by a spring. And if this weight is subject to a gravitational force, right, it becomes even more unstable. So this setup is relatively in a unstable position, and it is very sensitive to changes in gravitational acceleration. So that makes it an unstable type of gravimeter or a static. Okay, so introducing any form of force will further destabilize the position of your mass. So how does this work? Basically, you have your mass in here, and it is mainly suspended by a spring, what we call a zero length spring. Okay? So a zero length spring has a fancy definition, but all you have to remember is that a zero length spring is a spring that has a length which is proportional to the tensile forces due to gravity. So it means that its length can be easily converted into force due to gravity. Okay, so it has a predictable behavior, which which is the most important feature of a zero length spring. So so when this spring is elongating, it means that the gravitational force is getting stronger in here. Okay, the mass will be pulled down. You have a strong gravity, and the zero length spring will be stretched out. All right, now we know that the length of the zero length spring is proportional to the gravitational force, and we also know the mass of the object, so we can derive the gravitational acceleration. All right, but how do we exactly measure the gravitational acceleration? So we also have another spring here, which is called the measuring spring, right? And what we do is every time this zero length spring stretches, we try to rotate this dial so that the spring will go back to its normal length. Okay, and the number of turns that you do in this dial will reflect is calibrated to read out the relative gravitational acceleration. Okay, so it's quite a simple setup. Now, the typical usable accuracy of unstable gravimeters is in the range of 0.01 to zero point zero 0.02 milligals. Now, let's talk about the field survey. So I mentioned previously the reference or base stations or base nets or base networks, whatever you call it, as long as you call them base, all right, or reference. Uh, you won't be confused, all right? So base, and the keyword in base is you have two types. You have a primary base and a secondary base. Primary base, what they have is, so this is an example of a primary base or a primary gravity or a gravity base station. So this was established. This is being maintained by NAMRIA. So what you can find in a primary base is you have this marker, you have this physical marker, and it has an absolute gravity reading. It has an established absolute gravity reading, which is done by the survey team of NAMRIA. So you have here a surveyor who has a gravimeter, and they measure the absolute gravity in that area. And they also measure the elevation in that area. Okay, so primary base nets or first also called first tier base nets, they have an established absolute gravity reading, and they also have an accurate measure of elevation. Now we also have, since it's impractical to put primary base stations all over the area, we also have what we call secondary nets, which are linked to your primary base, right? So what they do here is they first calibrate their gravimeter in the primary base, and they do their relative gravity measurements in the secondary base, so that they can have an indirect, so they can actually have an indirect value of the absolute gravity in that station. Okay, so they tie the survey in the primary base to the secondary base. So primary base is all about direct reading of absolute gravity, while secondary nets are all about indirect reading of their absolute gravity value. All right. In surveys, it's sometimes it's not practical to go to these stations repeatedly. So sometimes what happens in gravity surveys is we just look for a primary gravity station and calibrate our instrument in that area. Then we go to when then we establish secondary base stations, all right, and we use them as our mainstay base stations throughout the survey. Okay, so Namibia maintains all these base stations. As of 2016, we have a total of 87 primary base stations around the Philippines, and we also have 1,624 secondary base stations. Okay, so this is a map of all the gravity stations in the Philippines. So it's quite small, but it's good to be aware that there is such thing as gravity base stations. Okay, and you have to visit that when you are doing a gravity survey to calibrate your equipment. Now let's talk about the bigger picture here, the scale of the survey and the instrument drift. The typical pattern of a gravity survey is a square grid. You have a grid of squares, and sorry, it's not a square, but and then we take gravity readings at the corners of your squares. Okay. Now, when you are talking about oil exploration, the size of that grid will be in order of zero point 0.5 to 1 kilometer. Okay. So we are talking about huge grids when you're talking about oil exploration. Now, for mineral or ore exploration, the typical stations are in the order of 10 to 50 meters. And then for general geology, like looking for formations or faults, the station spacing would be in between of these two. So it could be anywhere between 10 meters to 1 kilometer. Now we also have a term or a phenomenon called instrument drift. And this is important, okay? So remember that our gravity meter or gravimeter is relying on springs. Okay, springs. It is using springs, and these are metal springs, all right? And you know the property of metals when they are subjected to heat, all right? So when we are doing surveys, it's natural to be exposed to fluctuations of temperature, and it's not usual to be subject to temperature fluctuations exceeding 10 degrees Celsius. So that temperature fluctuation will of course impact the performance of your metal spring. So this will expand. So when your Doing a survey under high temperatures, the spring will expand, and you will be getting gravity readings that are erroneously high. Okay, so you have erroneously high gravity readings. All right, and there are other stuff that affects the performance of your spinning. Of course, you also have the constant tension caused by the weight. So the weight is constantly just trying to relax or trying to stretch out the spring, and little by little the spring will just creep out. It will extend permanently, little by little, through time. And of course, those things affect the value that you get from your gravimeter. And the most common remedy to that is to reoccupy the previously surveyed stations. Okay, so if I started, for example, if I started in this station, I went to the second station. Okay, the standard practice is to go back to this previous station after 1 or 2 hours to see how the gravity reading has changed since then. Okay, so that you can correct the reading in the next station. Or the more expensive solution is to simply have a second gravity unit, a second gravimeter. Okay, so you have one gravimeter doing the survey, and you also have a second gravimeter uh, just lying its ass on your base station. So you do your surveys here, you go around while this second gravimeter is just reading the same thing for like for the whole day. Okay, and you can definitely plot that. For example, this is your reference gravimeter that is just reading gravity at the same position for like 12 hours. Okay, so you are expecting ideally the reading of that gravimeter in that same position ideally should be constant because it's not really going anywhere. But of course, you have your instrument drift, you have your springs that are subject to heat and expanding, and you also have your springs that are relaxing due to constant tension. So the gravity reading will be increasing through time. You know, okay. So 12 hours, 24 hours, 36 hours, the reading is increasing and increasing. So what we can do is we just apply a mathematical correction. We obtain the trend of this line and subtract it from the data so that your data will just be more or less so that the reading at the reference station will be flat. Okay, and then you apply that to other readings you have done during the survey. Right, so that's one of the few things we do in the survey, but there are also other stuff that have to be accounted for in a gravity survey, and these are what we call the corrections. So the previous stuff about the drift is what we call the drift correction. Okay, so that's just one part of the corrections that we have to do. The first correction that we have to do is the polar flattening or the latitude correction. As discussed previously, the Earth is flat at the pole and bulging at the equator. Okay, and any north-south movements or north-south distances between your survey stations You have to correct that for latitude or polar flattening. Okay, so any survey stations that are closer to the North Pole or the South Pole, you can expect your gravity to be stronger. Okay, so if you have a big survey like exceeding 100 kilometers north south, you use the IGF formula. But if you're doing a small survey that's less than 100 kilometers north south, we can use this simpler formula. Okay, so the input here is just your latitude. So when you are close to the North Pole or South Pole, or the higher the latitudes are, you will have a more negative correction value. Correction value. Okay. This is because you're trying to compensate for the bigger gravity readings in the North Pole and the South Pole. So you're trying to remove that. Now the procedure to use this formula is first you calculate this value. So you first go to your base station. So you go to your base station, all right, and then you determine the latitude in that base station. So let's say the latitude is 51 degrees north. Okay. So if your latitude in that base station is 51 degrees north, then just plug that 51 degrees in this formula. All right. And then the value of that is around 8 GU. All right, per kilometers north. So if you did a survey, if your first survey point is, let's say this is your first survey point. So if your first survey point is located 0 kilometers north of your base station, okay, so then you don't need any correction, okay, for this survey station. Now, if you did another survey, let's say you did a second reading somewhere in north of your base station, and it is located 1 kilometer north, then you just multiply this negative 8 GU by the kilometers north of distance from that base station. So for survey station number 2, you need to apply a correction value of negative 8 gravity units. If you go further up north for survey station number 3, like 2 kilometers north, then you have to apply negative 16 gravity units. Now, if you move south, like 10 kilometers south, then you are dealing with negative kilometer values here. So you have to apply a correction value of 8 GU. Sorry, 80 positive 80 gravity units. All right. Now, let's talk about the other correction, which is the free air correction. So this accounts, it's in layman's terms, free air correction is just about the elevation. All right, but in the gravity survey jargon, they use elevation correction to describe free air correction plus the Bougie plate correction. Okay, so we are stuck with this free air correction term, but to laymanize, this is all about elevation. Okay, I personally hate the terminologies in gravity survey because they love to use a lot of confusing terms, and they love to use a lot of equations that are named after people. Okay, so yeah, it's quite intimidating. I mean, sometimes learning about gravity survey can be quite intimidating because it's full of jargon, it's full of names of famous people and so on, and it doesn't make sense to me personally. But it's just me, of course. So anyway, free air collection. You don't need to do free air collection if your readings are done at mean sea level. Okay, if you did your readings at the mean sea level, you don't need any free air collection. So if you did any readings that are above or below mean sea level, you have to do your free air correction. So if your elevation is lower than mean sea level, it means that your station, for example, this one, it means that your station is technically closer to the Earth. So you are subject to a stronger gravity, alright? And you have to correct that by subtracting, by using a negative correction value. Okay, so you use a negative correction value to counteract the stronger gravity reading you got in there. Now, if your reading was done at an elevation higher than your sea level, then your station is slightly away from the Earth, and therefore you have a weaker gravity. And to compensate for that, you have to add a positive correction value. All right. So the correction formula in here is this. So you just multiply the height in meters by 3.08 gravity units. So any elevation above sea level is positive, and any elevation below sea level is negative. So for example, if you did a survey that is done 10 meters above your mean sea level, then we'll just multiply, just plug in 10 meters in this formula, and you just all you have to do is just add a value of 30.86 gravity units in your reading in that station. Now, if you did another gravity reading, let's say somewhere in here, and it is like 20 meters below mean sea level, then just plug in negative 20 in this equation, and you will have a correction value of negative 61.72 gravity units. Right now, let's talk about the Bougie plate correction, or the correction for the material between the station and the sea level, or the geoid, supposedly quote unquote geoid. Okay, so this correction accounts for any material that is lying between your survey station and your mean sea level. So this correction is not necessary for readings that are done at mean sea level, so you don't need it if you did it at the sea level. It's also not necessary for readings that are done airborne, okay? Especially if, all right, if if the area you flew over is an open space. Like for example, you did an aerogravity, and basically the ground is at mean sea level. And this is also not necessary for readings that are done below mean sea level in an open space. So I'll just explain that briefly. So let's say this is your mean sea level, and that is also your ground elevation. So if you did a helicopter survey with a gravity, okay, basically there is no material between the mean sea level and your survey station, so you don't need a boogie plate correction. In the same manner, if let's say you are on a big valley, huge valley, all right? No, sorry. Let's say you are on an open area that is below mean sea level. So this is your MSL, and this is you doing survey. In here, in this case, technically there is no material lying between you and the mean sea level, so you don't need any boogie plate correction. Right now, going back, the free air correction is about the distance between the station and the mean sea level. So it's about the distance, while the boogie plate correction is about the material between the station and the mean sea level. So if there is no material, there is no rock or no soil that is sandwiched between the mean sea level and your survey station, then you don't need any boogie plate correction. But if there's any sort of material or rock or soil, then you have to do a boogie plate correction. And one of the important principles of this correction is that we assume that the rock or soil material between the station and the MSL is infinitely wide. Okay, so so let's look at this figure. For example, in this figure, all right. So the material between you and the station is technically a hill or a mountain. And in boogie plate correction, we just approximate this material as a plate and it's an infinitely wide plate. Okay, so this is our approximation for that correction. Okay, so that's you end up with this kind of assumption. Okay, we do that for the simplification of our calculations, right? And then, yeah, if your station is located above mean sea level, like a plateau, then it means that the rock or soil is positioned below. So the rock, so here, if your station is in here, then you have additional material in here. And this material is actually exerting additional gravity, additional downward gravitational acceleration on your station. So our compensation here is we use a negative correction value to remove that additional downward pull. Now, if your station is located in an underground like a cave, all right, then let's delete all this. So let's say you are, let's say this is mean sea level, and you are here Let's say you are on a cave or a tunnel. So what's happening here is that you have extra material between you and the mean sea level, but it is located above you. So so remember that gravitational acceleration acts on all directions. So this material is pulling things downward. It's also acting from the sides, and it's also pulling you upward. Okay, and the immediate effect of this material, of course, is that it is pulling you upward. So the extra material between you and the mean sea level is technically lifting you up. It's trying to lift you up and let you down. Sorry. So it's trying to lift you up. So in effect, it is technically countering the Earth's gravity. And the gravity reading that you will read in the station is slightly lower. Okay, so the correction here or the compensation is you add a positive correction value. All right. So now the formula for the Boogie plate correction is basically 2 pi times G times big G, sorry, times rho or the density of the Boogie plate or the rock or soil, and then the height or the thickness, right? If the material is below you and the convention for height is positive, oh, sorry. If the material is below you, the convention is that the height is negative. If the material is above you, and then the the sign of the height is positive. All right, then. All right, let's talk about the terrain correction, which gives me a headache. But what happens here is the local relief or terrain correction is a correction inception. So this is a correction for a correction. Okay, so terrain correction is a correction for the Bougie plate correction. Right, so what happens here is you see this familiar figure. Okay, so we just reversed the Bougie plate correction and the terrain correction. Okay, so we start with the Bougie plate correction and then we go back to the actual terrain, the details of the actual terrain. Okay, so we try to reverse the simplification done previously in the Boogie plate correction. Right, so remember that this correction is always done after the Boogie plate because obviously it's a correction for the Boogie plate correction. And remember that the Boogie plate correction assumes that the slab of rock or soil is infinitely wide and this is a slab. Okay, so it ignores all the effects of the local topography, and the job of the terrain correction is to put back again the effects of the local topography because the Boogie plate correction is too dumb to do that. Alright, so what happens here is we just compensate for all those local effects. Alright, for example, let's look at this figure. So this is this blue stuff is our Bougie plate correction, and this green area here is technically an empty space. Okay, but In the Boogie plate correction, it was assumed to be part of the Boogie plate. Okay. So this part, this airspace is technically not non-existent. Okay. And we call that a valley. Okay, so all the stuff that is non-existent in the Boogie plate is a valley. And the thing is, a non-existent material, sorry, a non-existent material is not exerting any additional downward force. All right. So the Boogie plate is wrong in that part. So to correct that wrong, we have to add a positive correction value corresponding to the to that valley. Right? So I'll show you the calculations later. And then let's go back again to the figure, and then if you would look at in this part, so on top of the Boogie plate, you also have extra stuff here. You have an extra stuff on top of your Boogie plate. Okay, you have an extra mass, and this is actually exerting. Sorry, so this is an extra mass, and it is located from above, and it's exerting a force from above, so it is technically pulling you up, right? So it's technically trying to fight you, trying to fight against the gravity by pulling you up. So technically, when there are hills or mountains near your station, uh, the the net gravitational force that you're experiencing is slightly smaller. All right. So to compensate for that, we add a positive correction value. Okay. So to recap, any material or any non-existent stuff that's in the that's inside the Boogie plate is a valley, and any extra stuff that's on top of the Boogie plate is a hill. Right now, in practice, what is typically done is this correction is normally done in software, and you have a lot of digital elevation models that can be used. You have your shuttle radar topography mission, or the SRTM. You also have the Aster GDEM, and you just feed that to your software and it will know how to do the corrections. Although note that in the field there are some discrepancies that you have to account for explicitly. For example, you have small valleys or small hills that are nearby your station. Although they might be small, but the fact that they are close to your station, they can exert a significant amount of gravitational influence on your station. So that has to be noted in the field, and it has to be calculated. And the stuff or the method or the tool that we use to calculate the topographic correction is the what we call the hammer chart. This hammer chart is basically a chart that is printed on a transparency. So if you're old enough to know what is an acetate, congrats. So this stuff is printed on an acetate, and then it has a printout of compartments and concentric rings, and you overlay that on the map. You center the chart on your station, and from there you try to calculate the volume. All right, you try to calculate the average relief, or sorry, you try to calculate the average topographic relief in that area. Okay, So let's say that the boogie plate that you are assuming is let's say that you found out that there is an extra mass in compartment number C, compartment C. Okay, you have a hill. Let's say you have a hill in there. All right. So let's say this is the size of the hill, and it has a height of 4 meters. Okay. So it has an average. This hill has an average height of 4 meters, and then the rest is just level ground. What we do here is we just average out. We try to take the weighted average of this compartment. We try to take the weighted average of the relief or the height of this compartment. So the hill is approximately occupying half of this zone of this compartment. So that would be approximately 2 meters or 1.9 meters, for example. So let's say the average height in that relief in that compartment is positive 1.9 meters, and it is lying on compartment C. So all you have to do is project that to the to this table, and you will get a correction value which is 0.01 gravity units. All right. So since it's a hill, you have to add that value, all right, to your gravity reading. Now there are other corrections. You also have what you call the building correction, although this stuff is not really properly established yet. I'll discuss it shortly. So to give you a context, traditionally gravity surveys was all about oil, ore, and geology. It's just a recent development that people are starting to use microgravity for engineering, environmental, and archaeological applications. Okay, for example, looking for sinkholes, looking at tunnel damages, looking for ancient tombs in urban areas. Okay, so let me just segue for a bit. Always remember uh, in geophysics, the industry on the top of the food chain is oil. Okay, oil has a lot of money. The oil industry has tons of money, and they can afford the most cutting edge technologies in their field. Okay, I would say oil industry is like 30 years ahead of the other fields of geophysics, is like 20 to 30 years ahead of, let's say, engineering in terms of geophysics. So the oil industry has a lot of money and has the best technology. The second industry riches is probably mining. So the technology just trickles down. Okay. Then you also have your geology and then your engineering. So So as time passes by, some of the cutting edge technologies in oil and mining industries become more affordable, so they trickle down to to the lesser industries like engineering and environmental and archaeology and so on. So that's generally how geophysics is developing recently. So it's just a trickle down effect from the richest industry to the poorest industry, right? So if you want to see the cutting edge, try to see the technologies used in the oil industries or in the mining industries. Anyway, so much for that segue. uh, for building corrections, all right? Especially if you're dealing with urban areas, note that buildings or outcrops in the vicinity can reduce the readings by zero point 0.1 to zero point 0.3 gravity units. So that's a significant amount. And to minimize the influence of buildings or outcrops, it is recommended to have your gravimeters positioned at least 2.5 meters away to limit their influence to zero point zero 0.05 gravity units. Now we also have correction, which is the influence of the tides or the influence of the sun and the moon on the earth. So the tides is a complex phenomenon that is due to the changing distances between the sun and the moon and the earth. As you can see in this GIF, they're essentially dancing around. Okay, so Earth is like is like a dancer that is spinning his little partner in here, while at the same time it is running around the sun. So it has a rather complex path, but it is predictable. Okay, so the tides are actually predictable, and you can get uh, a sort of an advanced schedule of the gravitational tide charts. Although, yeah, the influence of tides are quite significant. You can get as much as three gravity units of change due to tides. Although you have to note that there are a lot of other factors that affect your gravity survey readings. You have your instrument drift and the diurnal variations that affect your readings. And most of the time, it's actually just more convenient to just do a drift correction because it will take care of everything else, like your drift, your instrument drift, the diurnal variations, and also the tidal variations. Okay, so bottom line, drift corrections the are important. Now you also have another correction, which is what we call the Outpost correction. Sorry for the Hungarians. You have so Outpost is a Hungarian geophysicist. Okay, so yeah, geophysics love using names. They name equations after people. They name everything after people. But so Outpost correction is all about the corrections done for vehicles that are moving, like ships or airplanes. So this is relevant because remember previously that the geopotential or the acceleration due to the geopotential is due to gravity or the mass of the Earth and due to the centrifugal effects or due to the rotation of the Earth. So since the Earth is rotating constantly, and if you are doing a survey that involves relatively fast moving vehicles, all right, these vehicles are actually subject to the centrifugal force of the Earth. Okay, so it can either stack with the gravity that they are reading, or it can also cancel out. So it depends on the direction and the velocity of your sorry, it depends on the direction and the magnitude of the velocity, which is the speed of your vehicle. Right, so I won't be discussing this equation. I mean, I hate overloading people with equations, but if you need the equation, it's in there. You basically need the latitude of your survey and the direction or the azimuth of your flight path or your nautical path. And you also need the speed or the velocity of your vehicle. Now, finally, we will have, after all those corrections, Okay, so after doing all those corrections and after subtracting the gravity reading from the base station to get the relative to get relative readings, you finally have what we call the Boogie anomaly. So this is your final product. Yeah, I kind of fucking hate this term because it's always confusing. Say they have a Boogie plate correction for the correction, and they also have a Boogie plate anomaly for the final product. So Boogie anomaly is not Boogie plate correction. They're two different animals. They're not the same. It's confusing, but they are not the same. Alright, so Boogie anomaly is the final product, and more or less this is the product that we use for quantitative and qualitative interpretation. More or less, we sometimes we add some intermediate steps. All right, so to recap, negative anomalies negative are negative are negative differences relative to the base station. So it means that your area might be less dense than the base station. So there could be caves, or alterations like your clay alterations in ore deposits. Like, okay, so if you have a mafic country rock and it has alterations, normally the clay alterations are less dense than the mafic country rocks. Or if you have a salt dome in right, salt domes or salt is very very light, so it can register as a low density anomaly. Also, sedimentary basins are much less dense compared to basement rocks, right? Right now, positive anomalies means that the area is denser. Okay, so it could be vintage bombs, intrusions, and so on. Okay, so Boogie anomaly is basically corrections. So observed data and then the corrections, then minus the gravity reading at the base station. So corrections include latitude correction, free air correction, Boogie plate correction, terrain correction, Outpost correction, isostatic correction. So this is another stuff, but I won't be discussing that anymore. And you also have your drift corrections. Right now, we also have, let's discuss the interpretation of gravity. Now, when we are talking about interpretation of gravity, trends are important. And this is where the regionals and the residuals come into picture, right? So when we are talking about regionals and residuals, so these are all about the trends. And for example, look at this map. So this is a map of this is a contour map of gravity anomaly. Okay, so you can see here these are differences in gravity relative to the base station. So you have negative 265 GU, negative 260, negative 255, and so on. So this is all about anomalies, or this is a relative. This is a map showing the relative different the relative gravitational measurements in a given area. Okay, so definitely you are seeing lower gravitational values towards the north. So if you take a profile here, you do a profile. So you see here that in the north you have generally lower gravity readings. Okay, and it is just increasing and increasing towards the south. and then you get a hump. All right. Right, so these patterns can have a lot of explanations. This could be can be due to almost anything. But of course, when you're interpreting a gravity profile or a gravity contour, it has to be grounded on your geologic understanding of the area. So, for example, you have a geologic map. So, for example, you have a geologic map, and you know that this area is consisting of a sandstone formation. Okay, so let's say it's a sandstone formation. So let's say you know that this is a sandstone formation, or a dipping sandstone formation that is overlain by soil. So let's say that our model is like this. So you have a dipping sandstone formation that has a ridge. Okay, so this is the north, this is the south. And let's say that overlying the sandstone formation is just soil. So this is just soil. Okay. So naturally, if you're doing gravitational surveys, okay, so you take a reading here. The stuff that you read here is mostly just soil. So you will get a low gravity reading, and then as you go towards the south, you're getting closer and closer to the more dense sandstone unit. So it's increasing. And then in this part, you might encounter a ridge or a sort of a small fold in the sandstone formation. So it's actually exposed in that area, and the gravity reading jumps and then goes back again. All right. So let's say your geologic understanding of the area, and that is your initial interpretation. Now, the residuals and regionals take into picture depending on what's interesting to you or what is your objective. If you are just interested in the bigger picture, for example, this formation is actually continuing further. If you're just interested in the large scale dip of the formation, okay, you're what's important to you is the bigger trend, this line. So what you would be interested in is the regional or the regional trend. So that's what you need to extract. But if you are just interested in this fold, okay, let's say for example this fold might contain some, I don't know, might contain some intrusions or something else. Then you're only interested in this hump, okay, and your interest is just the residual. It's the residual component of the anomaly. Okay, so going back, so yeah, it depends on what you are interested in or what is your objective. If you want it once, okay, if you're looking at the big picture, you need the regional. If you're looking at a certain object, you need the residual. Now, separating those two is the tricky part. There is no unique or correct method of separating the regionals from the residuals. Although it's important to have a geological understanding of the area first before doing this extraction. Okay, because it it can go wrong in many ways. For example, you only took a profile in this part. Okay, so you only see this part and you think that I have two trends here, this trend and then this trend. Okay, so it's important to have a geological understanding of the area first before proceeding with these in-depth interpretations. So going back, there are many methods you can use to separate the regional from the residual. You can do some Fourier transform. You can do a polynomial line fitting, or my favorite is to just do a manual trend fit line fit. Okay, so what we do in manual trend line fit is we just trace this line. You try to draw a line that approximates the regional trend, and then we just get these the y is equal to mx plus b. Okay, so the y coordinate is equal to the slope of this line, or the rise over run, times the x coordinate plus the y-intercept. Okay, so it's that simple. So once you have that line, you can calculate the value of the regional throughout this plot, and then you can subtract this value from this anomaly profile, and you will get the final residual value. Okay, so once you've taken that, note that the residual value only represents that local object. Okay, mostly it's only representing that local object. Right, so just to discuss the residuals even further, once you have a residual trend of an air of your point of interest, you can do a lot of stuff with the residual anomaly. You can estimate the depth of the anomaly, or using the half-width method. You can also estimate the volume of the anomalous body using the Gauss theorem. Right. So uh, speaking of the volume and the depth of your anomalous bodies, the there are actually patterns that are associated with different 3D geometries of your anomalous objects. Okay, so this is done. These. Okay, so let's say you have, for example, a spherical buried object, like for example an ore body that is spherical in shape, right? So if you have a residual anomaly profile, the expected pattern of the anomaly is like this. It's like a nipple pointing upward. Okay, so your x-axis here is your gravity units in gravity units of the anomaly, and then your y-axis is your distance. Okay, so if you were able to do a gravity survey across that object, you will register this kind of residual anomaly profile. All right, and from there you can basically do a lot of stuff. Right, for example, you can start with the depth to the center of mass of this object. Okay, so at the start, it's difficult. If you don't have any much idea on the object, you can start with the depth to the center of mass, which is not the true depth of the material, but it's a good approximation. It's a good starting point. Now, if you know the density of the object, all right, you know, so let's say this is an ore body, and you know this is a propylitic alteration whatsoever. So let's say you know the alteration, what kind of alteration, what kind of materials are in there, and let's say you know that the density is 2.5 grams per cubic centimeter. And then from there, you can actually calculate the volume and the true depth of your object. Okay, you can do that with these anomaly patterns. Okay, so summary: if you know the shape of the anomalous body and you have a residual anomaly profile, and you know the density of the anomalous object, you can calculate the true depth and the volume of the object from your gravity data. Okay, so gravity can be powerful if you can constrain your investigation, which is true for all geophysical investigations. Okay, the limit of geophysical investigations is all about the constraints and the understanding that you have in the area. Right, so these are just examples of 3D geometries. So a sphere can be a cave, can be an ore body, and it looks like this one. A long horizontal cylinder can represent a horizontal tunnel, or a buried horse, or a buried graben, or a buried channel, or an undulation in your formation. Could be also a vein, or a dike, or a step structure, or bodies. A vertical cylinder can be an intrusive body, can be a salt dome, or a mine shaft. So mine shaft are just vertical holes. Right? A rectangular parallelepiped is basically a 3D rectangle with more or less unequal dimensions. So this shape is actually useful for almost any geologic feature except for features that have cubic dimensions. All right, so so this table is a good starting point on what shapes can you use to approximate a given problem or a given objective. Okay, so if you know the density of that anomalous object, more or less you can get a lot of details from your gravity anomaly. Right, so thanks for listening. These are my references. Milsum is important if you want to understand how all geophysical surveys work in the field. Okay, so there's a huge disconnect between the concept, between the theoretical part of geophysics and the field part of geophysics. I mean, yeah, I suggest you read that if you ever have to participate in a geophysical survey in the future. Parasnes is, I think, Parasnes is one of the most well-written geophysical books in the conceptual side. For me, uh, Kiri and Hill is just a rip-off of Parasnes. Okay, so all the concepts are beautifully explained and clearly written in Parasnes, in this Parasnes book. If you want to be familiar with the cutting edge, more or less the cutting edge or new technologies in geophysics, you can look at Reynolds. Right, so thanks for listening.